we can get started. So I took this poll last week, but I don't remember the precise answer. How many people here have taken quantum mechanics, undergraduate quantum mechanics? Good. Okay, so some of you might be a little bored, but no one complains about hearing Mozart. So if you hear something that you've heard before, that's not necessarily a bad thing. But first of all, we should start off with the really exciting news of the Nobel Prize in Physics that was awarded this week to Tholis, Haldane, and Kosterlitz for essentially studying what the goal of this lecture series is to try to explain to you, which is topological phases of matter. That may be just words at the moment, but hopefully at the end of this fall you'll have an idea of what that means. And as I said last week, the main focus of what I'm going to be talking about is building up to understanding the quantum Hall state. And the quantum Hall state is kind of the canonical example of the topological phase of matter. It's a highly non-trivial, strongly entangled, strongly interacting system that looks very different from normal phases of matter that you see via something like the Landau paradigm. So I'm not going to talk too much about the details of what they got their prizes for this week, but I want to tease that even next week I will be talking about at least some of the work that the Nobel was awarded for. But it's always validating to have your field get a Nobel. All right, so the topic today is quantum mechanics. So let's just take apart this word. Quantum, the idea is that particles, not just electrons, but also photons, any real microscopic particle comes in discrete quanta, right? You can have one photon or you can have 10 photons, but it has to be an integer number, okay? And mechanics is just the word we use to talk about describing how things behave, when you do things to them. You have an electron, you put it in an electric field or a magnetic field, and you want to ask what happens. So that's all this means. Quantum is often kind of used just to imply non-classicalness, and so you can kind of think of it a little bit divorced from this, original definition. But it originally came about when physicists noticed that there was this slight problem with blackbody radiation, delightfully called the ultraviolet catastrophe, probably one of the better names in physics. So if I just imagine I have regular classical electromagnetism, nice, smooth, plain waves, and you ask the following question. I have an object, it's at a finite temperature, it'll radiate, right? You see infrared cameras, that's infrared radiation radiating off of something that's hot. And the problem is that if you just go through, I'm not going to go through the details of it, but if you go through the standard classical textbook derivation, so B is essentially the intensity of the light you see, and lambda is the wavelength, and T is the temperature, this is the Boltzmann constant, the speed of light. It turns out, you go through the textbook derivation, and you see that it goes linearly with T, but it goes like the wavelength to the power -4, which means that if you ask about light at shorter and shorter wavelengths, it looks like it should be, blindingly hot. The idea is that, you light a match, and this formula tells you that that match is maybe making you a little bit warm from infrared radiation, but it's also bombarding you with a catastrophic amount of gamma rays, right? And that's obviously not what happens, right? We can light a match and not irradiate ourselves. And this problem was solved by Planck, who came up with this following theory. The idea is that light comes in individual packets called photons. And each one has an energy that goes as the inverse of its wavelength. And there is the speed of light and this important number h, Planck's constant, which is in either units of energy times time or momentum times position. And the important thing is that it's very, very small, right? So you have to zoom in really, really close to see this effect. And when you go through Planck's derivation, you find that indeed the formula for what the radiation looks like is drastically changed. This is just a messy looking formula. The important thing is that the answer looks very different. So this is a plot of, imagine something at about 5,000 Kelvin. That's roughly the temperature of the surface of the sun. And if you just use that original classical result called the Rayleigh-Jeans law, you find that the radiation intensity, this is a function of wavelength, so here are very short wavelength things and long wavelength things, it just blows up, and that's not what we see. What we see is essentially just this Planck radiation formula, and it turns out that since we're talking about the sun, its peak is essentially right in the, well, infrared to visible light range. And then, of course, it turns off because you can't be creating too many photons at really short wavelengths because it just costs too much energy. Because the energy isn't the size of the amplitude of your wave, because that's classical physics. The energy is the number of photons times the energy of each photon, and that's what basically cuts this off. And so what's happening here is that something that we thought was a nice, simple, classical wave is actually particle-like. Okay? So that's one thing that helped lead people to quantum mechanics. The other thing was something called the double slit experiment. You have a gun that shoots electrons, and you shoot it at a board that has 2 slits in it, and you ask, over here I have a detector, I'm going to shoot electrons one at a time, what am I going to see? So here's the top-down view of the same thing. And if I shoot an electron, well obviously it has to make it through one of these holes to get to the detector. So maybe it can go through the top, and I'd get a bunch of electrons measured here. Maybe it goes to the bottom, Maybe it goes to the bottom, I get a bunch of electrons here. And if we just think of these as classical particles, those are the only 2 ways that it can go through. So if you ask about, there's some fuzziness of these things not being infinitely narrow, you'd expect a classical distribution of particles to build up where there's going to be a whole bunch here, none in here, and a whole bunch over here. And unfortunately, that's not what you observe, right? What you observe is something that looks like an interference pattern. Right? It wiggles as I look along here, a lot of electrons here, very few electrons here, so on and so forth. And what this looks like is even though we're talking about electrons, not light anymore, this looks like wave mechanics in the following sense. If I asked about doing this problem with classical waves, water, you could do this water waves in a sink if you want. So here's, again, this picture. Here are my 2 slits. I'm going to be pushing waves through these 2 holes. Now, waves can either have constructive or destructive interference, right? So you can think of this picture as each of these lines is at the peak where the wave is the highest, and in between is where it's the lowest, okay? So what that means is that anytime the red and blue lines cross, the 2 waves add together and it looks even bigger, but if I'm in a region in between, where here the blue wave is very high but the red wave is very low, they basically cancel out to 0. And if you go through this carefully, you find that this interference will give you precisely this evenly spaced, bright and dark spots. Is this picture clear to everyone? Good. Now that's waves, but you can just ask the question, well, we're talking about electrons. I can have an electron gun that will shoot 1 electron at a time. And what happens, so this is actual experimental evidence, so this is a picture of the detector. Every white spot is where an electron hit. So here I had a bunch of electrons hit. Doesn't look too patterned. I start getting more. I start getting more. I start getting more. And you'll notice now this is experimental evidence that there are these lighter regions and darker regions. And so the electron, even though we like to think of it as a single point particle, is really wave-like. There's a sense in which the particle is going through both slits of the detector at once, just like in this picture, and it's interfering with itself in a wave-like way. And then this is what's called wave-particle duality. There are many senses in which you can think of particles as behaving like waves, as this electron did. You can think of waves behaving like particles, the way that you had electromagnetic light really looking like particles, individual particles made out of photons in the black body problem. Okay. So if particles are wave-like, we need to understand what type of waves are they. They're not classical waves. That's important. What they are, in quantum mechanics, what you'd like to think of as a particle isn't a point-like object with a definitive location and velocity. Instead, it's represented by a complex valued function of both time and space. And if you know this function, you know everything about what's going on. All of the information in the system is there. So here's just a crude picture of a generic wave packet I built. So you see this is the x direction, and I have the real part of the wave function and the imaginary part of the wave function. So everyone here is reasonably comfortable with complex numbers? Yes? If not, stop me, because I can explain it in more detail. Good. That's going to make my life much easier. All right. So it's you can always just think of complex numbers as, you know, it's like a vector. So these are what these objects look like. So let's think about some simple systems that we understand very well classically. A very canonical example is something like a ball on a spring. If I have a ball on a spring and I displace it away from where the spring is at rest, I know that there's a restorative force, which is basically some number called the string constant times the displacement amount. So if I take this ball and I stretch it out, it'll just wiggle back and forth. It's called a simple harmonic oscillator. It's very nice. If you want to talk about things that are really microscopic, not a ball on a spring, you can do the same thing with an electron. I can put the electron in a background electric field where all of the field lines are pointing in towards one direction. So if it sits in the middle, no forces act on it. But if I move it away from sitting dead center, the electric field pushes it back. If I move it here, the electric field pushes it back, and so forth. So these are all classical pictures because I'm talking about objects at points. And a fair question is, what's the quantum picture? And let's see if this animates correctly. So this is a plot of a particular wave function that corresponds to an electron in this electric trap. The blue curve is the real part of the wave function. The yellow curve is the imaginary part. And hopefully it will animate. There we go. So you see what happens, right? There's a sense in which you can still see it kind of sloshing back and forth. But it's not at a point anymore. And it's really evolving in some funny, strange way. Okay? Just do that one more time. Right? So you can see there's a sense in which it's sort of, if you squint, maybe looks like a ball on a spring because it's bouncing back and forth. But it's not at a single point. It kind of has some explicit width and range.
When they oppose each other, why?
So when what, the real and imaginary?
Why only the two waves are opposed to each other?
Good. Yes. So for instance, yeah, there's some regions in here where it looks like the imaginary part is positive and the real part is negative. But they don't interfere in that sense because it's a complex number. I'll get to this in a little bit. You can think of this as having, among other things in it, a probability distribution for where the electron is. And the probability distribution is the sum of the squares of the real part and the imaginary part. Because that's the amplitude of the complex number. So the real and imaginary parts don't interfere with each other in that sense. But, you know, I can't plot on a two-dimensional plane a complex function. So what are the rules that tell us how this thing behaves and why it does what it does? Well, there's a very, very famous equation called Schrodinger's equation. So we're going to take it apart. So psi, remember, is this complex valued wave function. And what Schrodinger's equation tells us is the following. If I take a time derivative of this, the time derivative is going to tell me basically if I know the wave function at one point in time, the time derivative tells me I know what it looks like one step forward in time. We'll get to that in details. And you see that this time derivative of the wave function is proportional to this object called the Hamiltonian, which is a measure of the total energy in the system. This p squared over 2m tells me about the kinetic energy in the system. And if I have external forces acting on it, then I also need to have a potential. The force is just the derivative of v. And so you can work out this is this formula. So it's clear that if I know this function at t equals 0, I calculate this, and that tells me what the wave function looks like one step forward in time. And that's exactly how I did that. I made that plot previously. So h, the Hamiltonian, is the total energy. This number p is the momentum. Momentum, remember, is just mass times velocity, so it's just keeping track of kind of how fast the particle is moving. And it turns out that momentum as an operator has this funny form. It looks like a derivative. It's not an independent variable. So, okay, this is what I was saying previously. If you're not super familiar with calculus, the important thing is the following. When I take, say, a derivative of a function with respect to some parameter, what that really is that it's the difference between the function one step forward in time as compared to where it is now, and you have to put these e's in there to make everything cancel out. But again, the idea is that this is just telling me I have the wave function at one point in time, what is it at the next point in time, so that I can talk about how the system evolves as I do things to it. The spatial derivative here is measuring basically how curved the wave function is. If it's very curved, it has a lot of kinetic energy. And as I said, V knows about external forces just by taking the spatial derivative of this. Okay, so this is very important. So I'm surprised no one asked me, why is taking this derivative have anything to do with momentum? It's a perfectly fair question. And there are kind of very technical explanations, and there are very pictorial explanations. So I'm going to give a pictorial explanation. If I just have a solution to Schrodinger's equation with no potential, it's just an oscillating plane wave. So it's exponential of some traveling wave packet. So remember, this is just something that always has a magnitude 1, and its phase, the phase of the complex number, is basically this junk in here. And you see that the frequency at which it's oscillating is related to this number k. And if you remember some basic things about classical physics, when I have behavior that looks like this, I identify this as a plane wave, so a wave that really is oscillating in all of space. And because of the fact that I have k times x and omega times t, I identify this number k as the momentum of this wave, and omega is its frequency. And you can just quickly calculate that if I act with this object p, this operator, that just takes a derivative with some additional factors, I get back k. So that's the sense in which this p acting on psi really is the right way to measure the momentum of a wave. But it's more general than that. Okay. So we have this complex valued function. The input is, you say, okay, I have, let's say, an electron, and I know its mass. That's what the m in the formula was. And I know that, for instance, I have some electric and magnetic fields turned on, and they show up in that potential V in the problem. What does it mean, right? And the answer is, sometimes people find it a little disappointing. It's really a statistical theory, right? Quantum mechanics is not a explicit, right? You don't know exactly what's going to happen, even though I said this wave function psi knows everything about the system. But if I actually go into a lab and try to do a measurement, what quantum mechanics tells me is probabilities of things I might see. And so in particular, the probability of finding a particle at a position x is just the magnitude squared of its wave function, which is just the wave function times its complex conjugate. So this is now a picture of the probability of where I'd expect electrons to be for that double slit experiment. And you'll notice that, okay, so red is where it's very likely, and then blue is where it's very unlikely. And you'll notice that if I just calculate what the probability was, I see that it's more likely here, less likely here. And this is precisely that interference pattern we talked about happening, except now it's really a probabilistic thing. So when you do that experiment with sending individual electrons through, the electron goes in here, wiggles around, and then it hits the detector, and with some probability, higher probabilities in the lighter than the darker regions, the electron will end up sitting there. Now, something that's very different from ordinary wave mechanics and quantum mechanics is that since we're interpreting this wave function as knowing, among other things, about probability distributions, we know that the sum of all probabilities has to be 1, right? And that constrains essentially the size of the wave function. So to those people who don't remember calculus, this little symbol right here means that this is some function, and I want to add up all of the area beneath it. So here's some probability distribution for some wave function. This is actually at some time the wave function I had animated earlier. And you'll notice that, okay, it's clearly much more likely to find the electron in here, where there's a lot of stuff, versus out here, where it's almost 0. But if I sum up the probability of it being at every single point in here, I have to get 1, right? So it's very different from classical waves. And there's, of course, more information than just this probability distribution. So let's talk about why this looks different. So if I was talking about classical probability theory, if I have a probability distribution, then you can calculate kind of statistical expectation values. But they look a little different in quantum mechanics, right? So an expectation value is basically the most likely thing you would measure if you measured some information about the system. So if I want to know where I am most likely to find the electron, it's just this, again, this integral of psi star x times psi. So the formula is basically whatever object is sitting in here, I sandwich it between psi star and psi, which means that if I ask about momentum, I have to put this derivative operator in there, right? If I wanted to ask about what's the average energy that I'd expect to measure, well, you just plug in the Hamiltonian. But again, this is all probabilistic. So without going into the details of a derivation, many of you have probably heard of the Heisenberg uncertainty principle, which tells you that there's some things you're not allowed to know precisely at the same time. The fundamental physics of why this is happening is the following. It's clear from the formulas that I wrote down previously that x times p is not the same thing as p times x, which is very unusual. If these were both just numbers, it would of course be 0, but they're not numbers. They're operators that act on the wave function in some non-trivial way, and you can go through a quick bit of calculus to see that the difference between x times p and p times x is proportional to h bar. H bar is just Planck's constant divided by a factor of 2 pi, because when you do quantum mechanics, you get all sorts of factors of 2 pi all over the place, and at some point it becomes easier to just absorb them into h. And a essentially consequence of this is that there's some things you can't know perfectly well at the same time. For instance, how well you can know where a particle is and its momentum is bounded. If I really want to know where that particle is, I can't know exactly how fast it's moving and vice versa. Similarly, if I want to know the energy of a system, I have to very, very accurately, I have to do a long time of measurements, essentially speaking, right? If I look very briefly, all of my energy readings are going to be essentially blurred. Okay, so this is a little puzzling, and let's just talk a little bit about the physics of it. And remember that h bar was this fundamental constant of nature that's very tiny. So let's go through 2 examples. So the pitcher that we stole from the Yankees, Aroldis Chapman, he could throw a baseball easily at 100 miles an hour, and a baseball weighs 149 grams. So if you take that, that's a mass times velocity. And if he's throwing it that fast, then the uncertainty principle tells us we can't know exactly where it is. Now, how well you can't know where it is very tiny. It's about 1.5 times 10 to the negative 34 meters. So that's because that's a big object. It's very classical, and so it's very hard to see this effect. All right? So again, this is a very small number. Now instead, imagine thinking about an actual atomic system, like have an electron transitioning from p shell to s shell in an atom. The momentum is this very small number, and what that basically means is that you can't see where the electron is to a size smaller than basically half an angstrom. An angstrom is, roughly speaking, the radius of a hydrogen atom, right? So large scales, you can more or less ignore this. It's not going to do anything. But if I start thinking about small scales, it becomes very important. And since we're talking about things like electrons, it is going to be very important. Are there any questions so far? All right, great. Okay. So if I can make this problem a little easier, right? Previously I had a formula that says if I know the wave function and I know the Hamiltonian, I know how that wave function evolves forward in time. We can actually do a little better because you're often not seeing precisely that, as I made reference to in terms of kind of spectra of a hydrogen atom. Often something that's more easy to measure is transition energies, right? You know, if I have an electron in one orbital of an atom and it transitions to another one, and a photon is emitted, and you measure the energy of that photon. We want to be able to do that type of calculation. So what you do is you say, if forces are constant in time, I can assume that the wave function is of the following form. It's some function of position times a nice exponential dependence in time. So this is really, the assumption here is that this is just some phase that's spinning in time. All right? So this is just an assumption that we make. If you go through and see what the consequences of this are, you'll see that this constant E that I put in here as a guess, well, this was the Hamiltonian, and so you see the Hamiltonian acting on psi is just E. The Hamiltonian was the measure of the total energy. So E is called E because it is the total energy of the system. And similarly, you'll find that, as we guessed, the time dependence is just this phase here. So these are very, very special types of solutions to Schrodinger's equation. They're stationary in the following sense, right? The only time dependence is pure phase. So if I ask about the probability distribution, the phase just drops out. So probability distributions are basically constant in time, and what's happening is that the phase of the wave function is oscillating at a frequency proportional to the energy of the state that I'm looking at. So let's go through a basic example. The hydrogen atom, and again, I'm not going to bore you with the details of how you do this calculation, it's very straightforward. Imagine you have an electron and it's just orbiting around one proton. Now, the proton is much, much heavier than an electron. I think it's something like 2,000 or 3,000 times as heavy. So we're just going to, for the time being, ignore the idea that the proton might be moving as well, and it's just some big, heavy, charged object that attracts the electron. You go through the work of calculating Schrodinger's equation at fixed energy, and you end up finding this very puzzling formula. There are an infinite number of energy levels around an electron, labeled by a positive integer n, and the energy of each of these ones is negative. It's negative in the sense that the electron is bound to this system, and I have to add additional energy to break the electron free and ionize the atom. And it's 13.6 electron volts times 1 over n squared. Okay. So pictorially, what does this look like? So here are kind of roughly two pictures. Here's a beautifully crude picture of, this is the electric potential from the hydrogen nucleus. And you'll find that there are a bunch of energy states. Here's n equals 1, 2, 3. The higher the n is, the closer the energy is to 0, and the bigger the support of the wave function is. It's kind of puffed out bigger. If I thought about what the details of the wave function looked like, in the top-down view, here's the ground state where the electron is at minus 13.6 eV. It can get excited once more to n equals 2, 3, 4, so on and so forth. Now, why is this actually useful? Well, imagine I had an electron. Well, imagine I just have something simple, like I have a hydrogen atom, and I want to hit it with photons. Okay? Well, if I give that photon precisely the right amount of energy, that is the energy difference between two of these levels, the hydrogen atom will absorb the photon, and the electron pop from one guy to the next. And then if I wait a little bit, eventually that electron might decay back down to its ground state, and another photon would be emitted. All right, and the formula for that is precisely this. And if you've ever seen hydrogen lines, by you just burn hydrogen, put it next to a prism, and you see that there are a bunch of lines, the energy of each of those lines is given by this very simple formula. I could translate this energy into a simple frequency if I wanted to. Is this clear? Okay.
So, relating this to what you said a few moments ago about the distribution being static, or I can't remember how you phrased it. It's
stationary.
Stationary.
Yeah. So these are very specific states. Now, something I should mention is, like, this might be addressing your problem, but it's something I should have said anyways, is that the state doesn't have to look like that, right? I could have a system where I basically have a superposition of electrons in different orbitals about the atom, and then it wouldn't be stationary. And if I looked at the time dependence of the probability distribution, it would be changing. Like that example I gave in the beginning of a particular state for a particle a mass on a spring, or an electron in an electric potential, right? I could tell you about states where it's just fixed and has a constant, or has a time-independent probability distribution, but those are very special states.
Maybe I shouldn't have related it to being stationary. I guess more the question is more this: am I to understand, or am I correct to understand, that since n can go to infinity, that although the probability may be very, 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 very tiny, like something times 10 to the minus 500, as I think Dr. Martin expressed it to me, that it never goes to zero, and if that, does that mean that this wave system should be thought of as describing the system as it relates to the entirety of space? In other words, is there some probability, theoretical, that an electron in a hydrogen atom in my fingertip might be detected over the course of the life of the universe on Mars or something like that?
So technically speaking, yes, but because of the uncertainty principle, when these n's are very, very large, their difference is really tiny, and the uncertainty principle tells you that to measure energy splittings of a really small scale, you have to measure things for a very, very long time. But this, of course, actually breaks down once things get too far out if the hydrogen isn't really isolated, right? Because the hydrogen in your finger isn't just a single hydrogen atom in vacuum, it's probably attached to a water molecule, right? And so that's actually a much, much more complicated system, and you have to keep track of more moving parts. Here, we're simplifying things greatly and just talking about one electron with nothing else around it, because we can actually do the calculation. And we can, at least, there's some experiments for the Lyman and Balmer series where you can actually explicitly see this. So it's technically true that if I had this electron in a vacuum, it maybe has some extremely small, but technically non-zero probability to be observed very, very far away. That's certainly true. And that's not even talking about the fact that these are only the bound states, the states that are kind of trapped near the hydrogen atom. I could also just have an electron with an energy above zero that's just flying away somewhere else, right? This is just particular examples trying to make reference to a very specific experiment. But yeah, it's one of those funny things about probability that in all of these cases, when you ask about the probability of where you'll find the electron, there's a very important difference between a probability being very, very small and a probability being zero. And in these examples here, it is never exactly zero. So there is some chance. Now, you might be able to make some argument that if you go out far enough, you'd have to wait longer than the lifetime of the universe to have a 50% chance of observing it, and you can kind of wiggle out of this problem that way. That's making things more complicated. All right, okay. Are there any other pictures or any other questions about this picture of the quantum wave nature of particles? Good. Okay, so now we're going to move on to something else that is going to start out sounding very weird, but is going to be able to help us cook up kind of much simpler examples. And that's this notion that electrons spin. They're not just, right, we know they're not point particles, but they have some angular momentum to them. And their angular momentum is 1/2 in units of Planck's constant. If you go and look at things carefully, you notice that h has units of angular momentum. And part of the quantum of quantum mechanics is that angular momentum is in fact quantized. So they have spin 1/2 in units of h bars. The 1/2, I mean, it's kind of an arbitrary normalization. What it really comes from is the fact, and I'll go through this example in more detail. If you take an electron and rotate it 360 degrees, the wave function does not come back to itself. It comes back to minus itself. And you have to do a full 720 degree rotation. That means going around twice before the system comes back to itself. Okay. Which is a little puzzling. So when we normally think of angular momentum, you have a picture of some ball, like a bowling ball, and it's spinning. And the axis along which it is spinning is the direction of the angular momentum, and how fast it's spinning tells me how big that angular momentum vector is. So this is the usual picture of angular momentum and rotations. And if you ask about what the rotation matrix for a vector looks like, so here I'm just going to talk about rotations along the x-axis. So I'm mixing y and z into each other. This is the formula for the rotation matrix. So you'll notice that if I do a rotation by pi, or 180 degrees, the matrix is a little complicated. For 2 pi, it's simple. It's the identity. So if I do a pi rotation along the x-axis, x, y, and z, x, of course, stays the same, because that's the axis on which I'm doing the rotation. But y goes to minus z, and z goes to y. I've exchanged those two directions, right? It's literally I have this, and I do that rotation by pi. If I do a 2 pi rotation, I simply come back to myself. Right? nice and simple. This is what normal angular momentum looks like when you have a real physical system. An electron spin isn't a vector in three-dimensional space. It's a two-component object. You can basically think of it as, in some basis, it is either spinning up or spinning down. This would be a spin plus 1/2 and spin minus 1/2 state. And it has to have this amount of angular momentum. And the rules for rotation, those kind of rotation matrices that told me how things transform, are very different and certainly a lot weirder. The rotation matrix, remember these are two-component objects. The rotation matrix along the x-axis has this funny form, and this fact that it now depends on the angle divided by 2 instead of just the angle is really where that half in the name spin half comes from. So let's look at a couple things. First of all, a 2-pi rotation changes the sign, as we said previously. Okay, so here the idea is that if I have an electron, it can be either spin up or spin down. Now, what does that mean? That means that I don't just have a probability distribution for where the electron is. I have a probability for where the electron is with spin up and for where the electron is with spin down. And the sum of both of those probabilities has to add up to 1. So to use crude nomenclature, I'm going to label the wave function for being spin up as u and spin down as d. Okay? So in a real system, these aren't just numbers, they're actually functions of where you are in space. And if I do a pi rotation, of course down and up get exchanged, which seems very puzzling. If I do a 2-pi rotation, so that's just a full 360-degree rotation, my wave functions do not come back to themselves. As I said previously, they come back to minus themselves, and it's a different state. If I go all the way and do a 4-pi rotation, I see that I do indeed come back to myself. And so there's a sense in which electrons are, you have to do things twice as much. This is related to the thing that I had said last week about how if I take an electron and I braid it around the other, that's like exchanging them, and the system gets a minus sign. That's the same physics as this thing here. And it gets weirder, because if you remember in this picture here, I said, well, it can be either spinning up or spinning down in, say, the z direction in our picture. Okay. So here, we're going to do this a little more carefully. I say, okay, the wave function has a spin up wave function and a spin wave down wave function. So if I just use a nice matrix vector basis, I can say plus z is 1, 0, minus z is 0, 1. That means that spin up and spin down for electrons are orthogonal to each other. They have 0 overlap, as opposed to, in of course, regular systems where spin up and spin down are the same thing, it's just a different amplitude. So if I have the z, x, and y basis, a bunch of very puzzling things happen. If I take the state where it's spin up in the z direction, plus down in the z direction, I actually get plus in the x direction. If there's a typo here, this of course should be a minus sign. If I take spin up minus spin down, I get minus the x direction. And similarly, if I throw in some factors of I, it turns out that up plus down is either left in the y direction or right in the y direction. So this is very, very different than the usual notion of angular momentum that we have, right? Usually angular momentum, you just add up all of the vectors of the individual angular momentum, and that's the total angular momentum. And that's just not how electrons work. It's very strange. It's sort of a little puzzling. But that's something that you can experimentally verify, is that this is how these things behave. So let's simplify our problem, right? Previously we had to keep track of 2 wave functions everywhere. So let's simplify our lives and just assume, for the time being, that the position dependence of the wave functions is something that we're going to fix. For instance, the electron is just in the s shell of hydrogen, and we're not going to try to excite it out of that state. All you then have to keep track of is the relative phases and amplitudes for the up or down spin. And again, because probability has to be conserved, the sums of the squares of these 2 complex numbers has to be 1, right? So if alpha is 1, if A is 1 and B is 0, then it's all spin up. If they're both equal, then it's pointing in the z direction, and so on and so forth. And these numbers, again, just give me the relative probabilities for measuring up or down spin. So I'm going to use the shorthand notation. Instead of writing out explicit vectors, I'm just going to write a plus means plus z, minus means minus z. This is the same formula as this. So something that I glossed over earlier that I want to talk about in more detail because I think this system is much simpler to think about. Right? All you have to do is keep track of two numbers. Is what does it mean when you measure something? Right? You've probably heard people say all the time in quantum mechanics, when you measure something, you have affected the system, you have changed it. You can't do measurements without affecting the system. And precisely what that means is the following. Okay, we have this probabilistic interpretation of the system. So if I have my state, A times up and B times down, then I say that, okay, if I can prepare this state, 100 times, and I sit down and I measure the spin 100 times, I would expect that 100 is a big enough number that, A squared gives me the fraction of them that were measured spin up, and B squared gives the fraction of them that were spin down. And since they square to 1, you see that that gives you everything. But that's this probabilistic interpretation. When you actually go into a lab and measure the spin of an electron, which is something you can very easily do, you have an electron gun, you basically shoot it through a magnetic field, and it either goes up or down depending on the spin. Say I started with this state, and I measure the spin, and that particular time, I find that that the spin was up. Well, the state is no longer in this linear combination anymore. Since I measured that it's up, the state is exactly up. So I've changed the system by doing a measurement, which is very, very different from the usual ways of thinking about things. And similarly, if I measured the spin one time and found that it was spin down, the state would change to be the down state. Okay? So this is an important idea. What if I want to keep track of more than one particle, right? So here I've always been talking about one electron floating around something like a hydrogen atom, because that's the easiest thing to keep track of. If we have more than one particle, you don't have multiple wave functions. What you actually have is one wave function that keeps track of every particle. So instead of just having a wave function that depends on, say a position, keeping track of one particle, it can depend on, arbitrary numbers of different positions. And if I have a whole bunch of different electrons, I can change my Hamiltonian so that they interact with each other. So I could have something simple, like say I have two electrons. Well, they're both charge minus, so there's an electrostatic force between them, and I can include that in the problem. There's no issues with extending quantum mechanics to talk about multiple particles, but you see things get very messy very quickly, right? I have to keep track of a whole bunch of things. So we're going to take a very simple example where we're just going to ask about keeping track of the spins of two electrons. We're not going to keep track of where exactly they are. All right, so if I have two electrons, the notation here is that plus means that both are spinning up, and so forth. Plus minus is one. The first is up, and the second one is down, so on and so forth. And this is the most general state I can have, where again, the sums of the squares of all of these numbers has to be 1, because all probabilities have to add up to 1. Now, as I said previously, if I measure a spin, I change the state. So I start with this state, and let's say I measure the spin of the first particle, and we find that it's up. The state changes, right? These particular pieces of it, where the first spin was down, have to get thrown away. You kill them, and you're just left with these two possibilities. But you'll notice that it's still not, trivial. The second state could still be spin down or spin up, because we tried to consider the most general thing possible. So a boring case would be that, just both of the electrons are both spinning pointing up, and let's put it right here. One is spin up and one is spin down, and that's it. Now, what this means is that it doesn't matter what I do, if I do any measurements to the first system, the second electron is always going to be pointing down, no matter what I do. If I consider something that's more complicated, like the first guy being up and the second guy being down, plus the first guy being down and the second guy being up, this linear superposition of two states, you find that they're entangled in the following sense. If I measure the spin of the first electron, that changes what the spin of the second electron was, right? they feel each other when they're entangled, or unentangled, as in this case, they really don't care about each other. So this is something that's significantly more special. And so these things that I call boring states, where there isn't any entanglement. For instance, if I have a really basic atomic insulator, which means I have a material and every electron is trapped really far deep down in a potential well because of the ionic lattice, they don't really have any entanglement because each electron is essentially isolated from every other one. They really don't talk to each other at all. These are unentangled. Topological phases, one of the key signatures of them, of these topological phases, is that they're often very highly entangled, right? The electrons are interacting with one another, and so what you do to one very strongly affects what you do to the other guys. And something that I just want to hammer home, I think is very important, is that this concept of entanglement is a purely quantum feature. It's something that just doesn't happen in classical systems. Now, why doesn't it happen in classical systems? In classical systems, you don't have this ability to write down superpositions of different configurations, right? If I had a classical electron, I would say, well, it is either spin up or spin down. Those are the two possibilities. Similarly, I'd say I have a particle, and it's at this point here, and it's not anywhere else. But in quantum systems, I can write down much more complicated states. Like I can say it's half up and half down. Or I can write down, half up down and half down up. So it's really a basic property of quantum mechanics. So I went through this significantly faster than I thought I would. But yeah, so that's the story if you just want to keep track of one electron. I talked a little bit about how you would talk about multiple electrons. What I'm hoping to talk about next week is basically the starting blocks of how you want to talk about multiple particles at the same time. Now, why is that important? Right, so as I said, if I have a very boring state where none of the electrons talk to each other, then you don't have to worry about these problems. But the systems that we're interested in particular, fractional quantum Hall states, are precisely systems where the interactions between different electrons are very important. And so we need to be able to understand how to talk about, in more general ways, systems that have lots of electrons together, and maybe they're talking to each other, maybe we're not. But we'll get started on that next week. Thank you. Sure, yeah. So the spins I talked about here, I cheated, and I just talked about spin half particles. This is the type of spin that electrons and muons and so forth have, right? Which is a very special type. Now, that's because we're talking about very, very tiny objects. And so the amount of angular momentum in one electron is fixed by Planck's constant, literally just h bar over 2. It's a tiny number. Now, if you have a physical macroscopic object, it has to be made up of, 10 to the 26 individual microscopic particles. And so when you have a number that big, you can't see the distinction between the fact that it really has to be, discretized, and it's not actually continuous. So if you actually sat down and said, I really build a ball out of a whole bunch of atoms, then it's certainly true that the number of distinct spins that the system can have is quantized. However, how are you going to tell the difference between 10 to the 26 and 10 to the 26 plus 1, right? That relative difference is just too tiny to ever actually measure. So you have to dig down and look at kind of individual microscopic particles, like photons. I didn't say this. Photons have spin 1 or spin minus 1, and they behave much more like those vectors. This kind of quantized, discretized nature of angular momentum is really only something you see at the tiniest levels because things do not behave like simple spinning tops anymore. They're just more complicated objects. Does that answer your question, Howard?
puzzle from the last class. I'm in a entanglement. All right, you got 2 electrons entangled. You change, you separate them by great distances. You change the state of this. It like almost instantaneously changes the other state.
Yep.
So, but then we talked about Einstein said information can't travel, and you said well, that's not information, but that is information.
You can, so when I said yeah, okay, so what I said last week is that indeed if you have this example of an entangled pair of electrons, we'll go to a slide where I have it down. If I have a pair of entangled electrons like this, then indeed, right, even if I take those electrons and I made them originally entangled, and I have some way of separating them without that entanglement decohering, right? So these are all models where I'm in a perfect vacuum with no additional noise. In the real world, if I try to do this, I have to kind of keep those electrons trapped and be as cold as possible, otherwise they won't just interact with each other, they'll also interact with the environment and change the structure. Ignoring that detail, it's certainly true that when you do the measurement, there's a sense in which it instantaneously changes the state very, very far away. That's true. But there's no way to send a message using that process, right? Because I just do a measurement and I see what I get, okay? I can't do a measurement to get a specific answer, therefore changing my friend's result to be what I want it to be. That's not how it works. You just have to make a measurement and project, but you can't send something happens, but you can't send a note to your friend that way, faster than the speed of light.
What about if you had, let's say, think of the bits and bytes, zeros and ones, 12 entangled electrons, and you already worked out the code a long time ago that when we have this combination of up and down, some you'll change, some you won't change, so they get the binary equivalent on the other side. When you change the states of some of those 12, and that now represents a message or a word.
So the point is that you don't get to choose what you change the states to. There's just a probability that it'll turn into one thing versus the other. So in this case here, if I just think of this messy example up here, there's when I do the measurement once, and I measure the first guy, there is a probability, basically a squared plus b squared, that my first electron is spin up, and c squared plus d squared, that the first electron is down. I can't do a measurement that makes it specifically one of those. If you could, then absolutely you could use that to take signals, but that's just not how the game works.
That's the key.
Yep.
Earlier you mentioned when you're making a measurement the word kill. So then, is that like, will the rest of the states collapse then? Is that what you were kind of saying?
Yeah, I guess I probably shouldn't have been quite so dramatic. But yeah, the idea is that, and being a little blasé here, that indeed, right, if I have this particular state where I have some probability to have any of these configurations, and I measure the first spin, and I see that it's spin up, and then indeed basically what happens is I go from this state that has support in all 4 possibilities, and these last 2 guys just disappear. I only have support in the first 2 possibilities because I measured that the spin was up, so the spin has to be up. So I can't have any probability to get this state or this state. Yeah.
I guess related to the last 2 questions, is this probably not, as a layperson, I don't quite understand. I'm referring to this so-called, this is using your lingo, this so-called time evolution and the Schrodingers Equation evolution and how where is this difficult of trying to define superposition using 2 different definitions. I mean, the instant you start measuring or you measure something, is one thing, but yet it's that same sort of definition that sort of describes or is equivalent to superposition equation. And I just don't quite understand as a layperson.
So the idea of superposition is kind of the fundamental piece of quantum mechanics. If I go back to not talking about spins, maybe that's a little bit subtle. Let's go back to a picture of a wave function. So what is this? This is the wave function. Now, if we were just talking about classical physics, and you ask about a particle, forces are acting on it, that particle always exists at a specific point, okay? And in quantum mechanics, that's not the case, right? You see that there is, some probability that it's here, and some probability that it's here. It's kind of extended. Now, just like with spin, if I actually go in and look and say, where is the particle? What ends up happening after I do a measurement and I find where that particle is, the wave function no longer looks like this anymore, right? It's going to be just something that's extremely sharply peaked where you found it. And then you can ask, how does that system continue to evolve? And generically what happens is that if I saw it at one point and I wait a little bit, it'll go from being very sharply peaked about where I measured it, and then it'll kind of spread out in space again. It'll look more like this. So it's a little weird and can be tricky to wrap your head around, but yeah, the basic idea is the following. If I'm not actively trying to measure things about the system, Schrodinger's equation tells me how it evolves. If I do a measurement, then after doing that measurement, I've explicitly changed the state in a very different way than the way Schrodinger's equation tells me how it evolves. And it has to be in precisely the state that I saw it in. So similarly, if you measure the energy of a photon, right, then it goes from maybe being some non-trivial coherent sum of different photons with different wave functions to precisely the energy that you saw it in, or maybe more explicitly, here, right, each one of these tells me that once the electron hit the detector and I measured it, then the electron is no longer a non-trivial wave. It is stuck there on the board at that particular point. That's the weird thing about measurement. It's weird. It can be very counterintuitive at first, but it's just the way things work, right? You have to sit down and try to, you can try to philosophize about it, or you can just say, hey, look, you do a calculation in quantum mechanics, this is what you predict, this is what we see. That's what physics' job is, right? It's not to make things feel, warm and fuzzy, it's to tell you what you measure in the lab.
Do you have any guesses about why the measurement causes the collapse of the wave function?
Okay, so this is a dicey topic because it can very quickly veer into philosophy. There is a story about decoherence where you say that when you measure something, that means that you take your system and you couple it to a measuring apparatus. Okay? So if you have ever heard of the many worlds possibility, there's some words that maybe you shouldn't spend too much time worrying about. The idea is the following. Okay, so say I'm measuring the spin of an electron. So that means I have a device, and the device will either say up or down. So if I actually try to set up within the framework of quantum mechanics the way in which I would do the measurement, what ends up happening is that when I couple the two things, there are basically four states, and it's more or less the four states that I talked about at the end here. Where am I? Here we go, good. So we're going to use this type of language, except say the first spin is the actual spin of the electron you're trying to measure, and the second spin is really just the signal on what the device says. Okay? So if I do an actual measurement, and you just try to write down a basic way of coupling these things, and I turn on measuring, Schrodinger's equation will basically tell me that this coefficient goes to 0 very quickly, and this coefficient goes to 0 very quickly. So you are in a superposition of the spin was up and I measured up, or the spin was down and I measured down. And this is what's sometimes thought of as the many worlds possibility, that these two guys are basically independent of each other, and so it's kind of both up and I measured up and down and I measured down. But when you actually do this in a lab, you don't see this because you were stuck in one of these worlds, roughly speaking. But you can also just think of this as it's one of the rules for how you calculate things, is that if I do an actual measurement and I get an actual answer, I'm projected into being just in that state and everything else is 0.
So the result of a quantum mechanical prediction is always a probability.
Yes.
Probability is a pure number. the probability is the square of an amplitude. Its square root, therefore, must also be a pure number. And the amplitude is just one particular wave height at a particular phase. So the other wave heights at other phases are also pure numbers, I think. And so basically, it starts to look like the waves are waves of pure numbers, and you have them going through two slits through space, which now starts to look like waves of pure numbers moving through space, which seems very Neoplatonic. So where are the waves? Are they really existing in space? And are they just pure numbers insofar as they relate to the probability of any one thing you're trying to measure, whether it's position or spin or anything else?
Good. So indeed, right, I had this object, I called it the quantum mechanical wave function, and I said that among other things you could do with it, I could take its amplitude, its magnitude squared, and interpret that as a probability distribution, right? But that's not all of the information in the wave function. And so, for instance, if I wanted to calculate expectation values, or look at how the system responds to different behaviors, I need more than just the probability distribution. For instance, when I calculated the expectation value of the momentum of the state, right, it was not the probability distribution times some function, right? It was, I had to act with the derivative operator, and so I needed to know the full wave function, not just its amplitude. So you really, to be able to make a claim about anything that you could possibly measure about that particular electron, you need to know the full wave function, not just its amplitude squared. So, and in terms of, I wouldn't think of these as waves in the normal way of thinking of, waves in water, density waves, right, where you have some medium and then there's something carrying it around. The real way to think about this is that you thought you had, say, an electron and it was a point particle, but when you zoom in, it's just fuzzy, right? And you need some mathematical way of describing the shape of its fuzziness. And that's what the wave function is. It's not a classical wave propagating in some medium.
Is the momentum, is that a prediction that you make on a probabilistic basis? So does the wave function tell me what the likely momentum, or
Yes.
the distribution of possible momentums?
Yes. But it's a going from having the wave function in position space to calculating a probability distribution in velocity or momentum space is a non-trivial thing that I skipped because it's just a bunch of math. But there's a way of doing it, but you can't just know the position space probability distribution to derive the momentum space or velocity space distribution. You need, again, the whole wave function to go from one to the other. So that's the sense in which you really do need to know more than just some classical probability distribution to measure, to say what you might probabilistically measure for other things.
Well, not to try to insist too much, but it just sounds to me, because I'm not that adept at math, particularly probability math, it sounds to me like you're saying that there's three different probabilities, let's say position, momentum, and whatever else, spin, let's say. And so you're still talking about, it still seems to me like you would still be talking about number waves. And the question remains then, are these just, where are they? Do they really exist in space as opposed to functions consisting of rules in the minds of the physicist? Or
so I think the interference experiments make it very clear that these are waves that exist in space. And I want to emphasize a difference, right? So here, I talked about a wave function that depended on position. So if you do kind of classical probabilistic mechanics, you have a probability distribution that is a function of both position and momentum at the same time. And so you can talk about a classical, I don't know exactly where it is or how fast it's moving, so I can imagine some probability distribution of a classical particle moving. But there I can talk about x and p at the same time. And in quantum mechanical systems, you just can't. Because you can't know both x and p precisely. There's this uncertainty bound. And so you have to either work with X or P, but I can't use both at the same time. So it really is distinct from kind of classical probability distributions for classical particles. Yeah.
Again, this is a simple question from a layperson. Last week you talked about using linear algebra for today's talk. I get that, but I'm sort of trying to connect that with the problem of uncertainty and sort of tie that with how Schrodinger approached these problems of uncertainty versus de Broglie or de Broglie, depending on how you pronounce it. How would de Broglie have come up with a way or a formula or an equation to handle this problem of come up with an equation to tell you the probability location of a given?
I'm not sure. I'm not a scientific historian. But I mean, what I can tell you is that if you talk about what you measure in the lab when doing, for instance, these interference experiments or measuring the intensity of radiation from a hot object, if you try to do those calculations using standard classical physics methods, you get the wrong answer. If you do the calculation using basically the quantum mechanics rules that I told you about today, you get the right answer. So from that point of view, quantum mechanics is just a fact. It's a confusing fact, but it's just the way things work when you look at very, very small scales. Remember, in the example I gave for instance, the uncertainty principle, right? If you talk about an everyday object like someone throwing a baseball, the kind of amount of uncertainty there is something that you're never going to measure. But when I work at atomic scales, it's an actual physical thing that you see, right? You see this amount of uncertainty there.
I was thinking, if you had an experiment, you want to measure the position and the momentum of an electron, and you put it in perfect, absolute zero box. I know we can only come within a million of three, but let's say we could. With absolute zero, with a perfect vacuum, would you not then be able to measure exactly?
Nope.
Still would not?
Nope. So what would happen is that, say you have the particle in a box, it has some probability distribution for whatever the shape of the box is, okay? So then you go in and you measure it. So say you measure its position in the box, right? That changes it, and it is now, at least for that moment, its wave function is just extremely sharply peaked about where you saw it, right? And it turns out that it's not obvious that if it has a very, very sharp peak in position space, then if you go through the calculations of going from probability distributions in position space to velocity space, you'll find that the probability distribution is extremely wide in velocity space. So having seen where it is very, very sharply in position space, it's really not, it's extremely broad in kind of what possible velocities it could have, and vice versa.
Okay.
There are no more questions? Yep.
If I have two widely separated entangled particles and you make a measurement on one of them, does that completely destroy the entanglement?
It depends on the state. If the two guys were entangled, and then you make a measurement, you have to go through the projection and see what you got. So for instance, in this example here, you know, I measured the first spin, but it's still a non-trivial state. The second spin can still be plus or minus because I tried to write down the most general thing possible.
So they still could be.
They still could be entangled.
So, you talk about decoherence out of a superposed position. You talk about projection out of a superposed. Dirac calls it jumping. So it's a question of how does the system get out of superposition into a single state. So it's a how question. Does quantum mechanics have an answer to how that happens? The second how question is when the electron, entangled electrons at a distance, measuring one changes the state of the other instantaneously. And it's not an answer to the how question to say you could never use it to transport information. It's just a simple, pure science. Does quantum mechanics have an answer for how that happens? Force says there's an influence. That's kind of fuzzy.
Yeah, I mean, the answer at a mathematical level is precisely this method of projection. Now, that's not a very satisfying answer because it's not really a pictorial way of looking at things. If you go through and carefully cook up a model where I couple my electron to a measuring apparatus and work through the decoherence problem, well, you might run into this issue of having to deal with the many worlds interpretation. But there, it's all just following the standard rules of quantum mechanics, or you can take the direct like projection result where you say you have to see what you measured, and now you know what state the system is in. I mean, again, since I'm not a philosopher, I'm not sure what more I can say other than those are the rules for the mathematical framework of describing the system, and they work in the sense that they agree with experiment. They may be disquieting, right? They may seem very weird and unintuitive, because that's not the way that things we usually interact with behave, but it is the way that electrons behave, and that's just a fact. It's a confusing fact, but it's just a fact.